Hello, we've got an example for Chapter 5, Equilibrium of a Rigid Body. We have two forces, one acting at a 45-degree angle of 600 newtons, 2 meters away from point A, and we have a 200 Newton force acting right on top of point B, and we also have a 100 Newton meter force acting down 5 meters away from point A or 2 meters from point B. So the first thing we're going to do, our process here, is we're going to draw our free body diagram, and then we're going to use our equilibrium equations to solve for our reaction forces. So this will be our find is our reaction forces. Now part of this is knowing what reaction forces that you're looking at. So let's go ahead and draw our free body diagram. On our left, at point A, we have a force that's going to be acting in the y direction that we will call AY. And at point B, pin connection, we will have BY and BX. Now notice how I drew it to the left because I see that the 600 Newton force is going to the right. So I am saying that this is going left, and I'll show you positive, negatives, and what that all means here in a little bit. I'm going to break up my 600 Newton force right away, and I'm going to draw one this way, and I'm going to draw one this way. And this is going to be 600 cosine 45. And this is going to be 600 sine 45. And then I have my 100 Newton force acting here, and I have my 200 Newton force acting here. Now could I draw this on the top of the beam? Absolutely, it doesn't matter for our calculations. Now I'm going to go ahead and put my distances in. Remember, when you annotate your free body diagram, you must annotate everything. So I'm going to have 2 meters, 3 meters, and 2 meters. Okay. So I drew my free body diagram. And now I am going to use number 2 and use the equilibrium equations to solve for my reaction forces. My equilibrium equations are summing my forces in the y. These are just my equations. Summing my forces in the x. And summing my moment at a point. Those are my equilibrium equations. So let's go ahead, and if I sum my forces in the y right now, so if I had AY minus 600 sine 45 minus 100 minus 200 plus BY, that's a BY, I have two unknowns. I could sum my forces in the x, I just have BX and 600 cosine 45. So let's do that. So if I sum my forces in the x direction, I can get an answer. So I'm going to have 600 cosine 45 degrees minus bx, because that is going left, is equal to 0. Now if I take bx to the other side, I get that bx is going to equal 424.2 newtons. So there's one. Now, since I said it was going negative, I have assumed that it was going left. My answer came out positive, so my assumption that Bx is going left to hold this beam in equilibrium is true, so I leave it alone. Okay, now, again, since I sum my forces in the y, I would have two unknowns. Let's sum my moment at a certain point. So I'm going to sum my moment at a point. Now, could I do it about point B? Sure, I get rid of By and Bx and 200 newtons because they're all going into that point. I could sum my moment at point A. That gets rid of this AY And since the 600 cosine 45 is in the x direction, no matter where we sum our moment about point B or point A, it does not matter because this is not going to have an effect. Now, if I sum my moment about a point here or here or here or anywhere else on this beam, again, I will have two unknowns. So I pick a point where the reaction force is going directly into it, so that the way the distance, the perpendicular distance, would be 0, so it would cancel that out. I went ahead and summed my moment about point A because that's just typically what I do. I start at the left-hand side. So I have 600 cosine 45 is my first force that I run into that I must take into account. It is rotating clockwise, so it would be negative. So 600, and that's going to be sine of 45. Now my moment, again, remember my moment is force, which I have here, times my distance. So my distance here is going to be 2 meters. So that's going to be newtons, and this is going to be 2 meters. This 100 Newton force is also acting negative, minus 100 newtons. Now you notice the distance from point A to this point at 100 newtons is 5 meters. So I'm going to say times 5 meters. Let's just do this. Times 5 meters. Then I run into the 200 Newton force. Again, it's 200 newtons, negative, times this full distance, which is 7 meters. And what we're solving for, By. But By is rotating counterclockwise, which is going to be positive. So plus By times the total distance. Remember, it is a moment. You're taking the moment of By, so it is also 7 meters here. And this is all equal to 0. So plugging this into your calculator, you will get negative 848.5 Newton meters, and that was negative, that's this piece here, minus 500 Newton meters, minus 1400 Newton meters, equals, now if I take this over to the other side, it would be negative 7 By. Now, using algebra, I can see if I multiplied everything by negative, everything becomes positive. So I could say that if I sum these all up, I could get 2748.5, and that would be negative 7 By. If I divide it by a negative 7 divided by a negative 7, I would also get that By comes out to be 392.6 newtons. So now I have solved for Bx and By. So I have these two. So the last thing I need to find is Ay, the reaction force, in order to keep this in equilibrium. So simply I do sum my forces in the y is equal to 0. If I sum my forces in the y, I got Ay minus 600 sine of 45 minus 100 newtons minus 200 newtons plus By, which I got was 392.6 plus 392.6 newtons. Again, remember, I assumed that it was positive. It came out positive, so that is correct, okay? And that's all equal to 0. So plugging this into my calculator, I'm going to come up with that Ay is 331.7 newtons. Now going back and looking at my forces, I have 200 Newton force here, I have 100 Newton forces here, so I have about 300 Newton forces acting over here at By, plus this 600 Newtons that's kind of acting at an angle over here. So does 392.6 Newtons look pretty good? Yes, to me it does. Ay, I've got the 600 Newtons, 45-degree angle, plus a little bit of this over here, 331.7 Newtons. Yes, so with common sense, these reaction forces look like they should be correct. Okay, I'm going to stop this one, and I will do 2 more examples to help out with reaction forces. Remember, moving forward, reaction forces will be very important to the class in order to solve the remainder of what we'll be doing in class. You must be able to solve for reaction forces. So if you have questions, please post them on the discussion board so that way we can have a discussion on those. Try to refrain from sending me Canvas inbox messages. Put them on the discussion page so we can discuss them there. Thank you.